Okay, so for number one, describe the motion. I got that the object is stationary from 0 to 1 second, then it starts to move with constant speed from 1 to 3 seconds, then finally move with a slower speed from 3 to 5 seconds. So basically, as you can see, uh, from 0 to 1, the position doesn't change at all. The slopes stay 0, and then starting from 1 to 3, the position go from 2 to 8, and then from 3 to 5, the position change from 8 to 10. Um, so the velocity is constant at 1 to 3 and from 3 to 5, because basically by looking at the graph, you can see that the slope of the graph from 1 to 3 is um is straight, and from 3 to 5 is also straight. So that tells me that the velocity is going to be constant from 1 to 3 and from 3 to 5. From 0 to 1, the slope is 0, therefore you can say that the velocity is constant too, which is 0. Um, so find the object instantaneous velocity at each of the following time. So basically from 0 to 1 second, the object doesn't move, therefore it doesn't have any uh velocity, instantaneous velocity. Then instantaneous velocity should be 0 from 0 to 1. And then from 1 to 3, I use the formula velocity equal to the change in position over the change in time. And from 1 to 3, I got 3 meter per second. You can also do it using calculus by uh, obtaining the slope of the line from 1 to 3 of the position versus time graph. Then you would get velocity versus time. Uh, Similar for part 3, which is the instantaneous velocity at 4 seconds. I got the velocity to be equal to 1 using the fact that the slope from 3 to 5 is 1 of the position for time graph. So how does the method you used from part 1 to 3 rely on your answer to part A? So basically, I know that for part A, the position is changing as a constant rate, which means that the instantaneous velocity is going to be equal to the average velocity at that specific interval. So basically from 0 to 1, the average velocity is going to be equal to 0 during that interval, and also the instantaneous velocity as well, since the object is moving with constant velocity during the interval. Therefore, the instantaneous velocity is equal to the average velocity. So for each of the following interval, find the average velocity of the object between A and C. Also, basically, to find the average velocity from A to C, I drew a line going from A to C, and then find the slope of that line, which give me the velocity, the average velocity from A to C. Or you can use the formula V average equal to the change in displacement over the time interval for the change, which will give you the same answer. So similar for A to D. So this is the line from A to D, and I found the slope to be a fifth, A over 5 meter per second. And then for from B to D, this is the line from B to D, the slope of that line is 2 meters per second, so that would be like the average velocity. Okay. So basically the slope of the line that I drew is the same as the average velocity of that interval. So basically the slope is the average velocity. So the average for part D, the average distance from B to D is equal to 1/2 of the average velocity from B to C at and C to D. Okay, number 2A. In the interval from t equals 0 second to t equals 6 second, does the object move with nearly constant velocity or definitely varying velocity? So I got that the object is moving with varying velocity because as I was interpreting the position versus time graph, I can see that this is a parabola. So basically, the object is starting in the positive direction, then slowing down to a stop, and then it turn around and start to move backward in the same direction where it came from. So the fact that it was like moving fast at first and then slowing down to a stop showed the inconsistency in the velocity. You can interpret that by calculus using the slope of the parabola too. So at first, the slope of the graph is really steep, and then as you approaching the minimum, you can see that the graph starting to become shallower and then eventually go to 0. So basically, the velocity was really negative at first, then starting to become less negative, then become 0, then go to positive, more positive. So which means that the velocity is not constant over the interval. So for part B, it's just I just plug in value into the graph, and I got a straight line. Part C is really similar. I also got a straight line with a negative slope going down by plugging in the value. So for part D, how can you account for the last graph to be so much straighter than the first? So basically, if we draw a tangent line to the parabola at a certain point, so a tangent line to a parabola at this point, then we expand the interval, like going to even a smaller t, then we would actually see that the slope of the parabola is equal to the slope of the tangent line. So basically, the slope at that point is going to be equal to the slope of the tangent point that is going to intersect that point. And the last graph, which you can see here, is a representation of the tangent line instead of this curve. So that explains why this graph is so much straighter than the first. So can you tell from a very small interval on the graph whether the motion over the whole graph has constant velocity? So I say no, you cannot. As we expand the graph and taking the limit as delta t becomes smaller and smaller, we would obtain an instantaneous velocity at that particular point And the instantaneous velocity can only tell us the velocity at that time instead of the whole graph. So this is a definition, a calculus definition of instantaneous velocity. So find the average velocity over the small time interval from 1.95 seconds to 2.05 seconds. Show your work and explain your reasoning. So I use the formula V average is equal to the displacement over the change in time. So I got that the V average turned out to be -2 centimeter per second, and the average velocity is equal to the instantaneous velocity at 2 seconds. Because as we make delta t smaller and smaller, which is taking the limit as t going to 0, or delta t going to 0, we got that the V average is actually equal to like the V instantaneous. Okay, so for number 3, part A, I got that point C would be correct because if the object was to move at constant velocity, then it would end up at point B at time delta t over 2. However, since the object is speeding up, which means that at delta t over 2 at the same period, the object would cover more distance, which is point C, farther than point B. Similarly, for part B, I got that point A would correspond to the location of the object at time delta t over 2. So, same idea. If the object was to move at constant velocity, it would end up at point B. However, it is slowing down, so the distance covered is going to be less than B, which is A. So it's going to end up at point A. Number 4. So most cars have a speedometer, odometer, and a clock. So part A describes how you could use the device to determine the instantaneous speed. So basically, for instantaneous speed, you would use a speedometer. You can just look at the speed at like a certain time, and that would tell you the speed at that time only. And this is also the definition of instantaneous velocity, which means the velocity at that instant of time. So part B, describe how you could use the devices to determine the average speed. So basically, to determine the average speed, you need the formula delta x equal to v multiplied by delta t. So in this case, we can use the odometer to find the total distance traveled or the displacement, and then we can use the clock to determine the total time elapsed for it to travel that distance. So you already know the delta t and delta x, then you can solve for v, which is the average velocity over that period of time.